In part two of load switch design, we'll replace the ideal enable switches with transistors and look into some of the key items driving part choice decisions. We can start with a MOSFET-based design for the enable switch. Since a 3.3 volt powered microcontroller is driving the gate of the FET, we need to select a logic level MOSFET. Logic level FETs have a threshold voltage that can range from zero point 0.6 to 2 volts or so. Every specific part has a slightly different characteristic, so you have to check the datasheet. The threshold voltage varies quite a bit with parameters like temperature, but for now we're looking at nominal performance. When using the transistor as a switch, you also want to overdrive the threshold voltage to ensure a good turn on. So for these reasons, the variation over temperature and the need for overdrive, FETs with a listed max threshold over 2 volts aren't great choices for 3.3 volt gate drive. Standard FETs have between 2 and 4 volt nominal threshold range, and they're good choices when you have somewhere between 8 and 12 volts available to drive the gate. There are still quite a few parts that are kind of in between with a max threshold voltage between 2 and 3 volts, and these should be avoided with a 3.3 volt rail. So we know we need to choose a logic level part, and then the other thing we'll take a look at is what the driver inside the microcontroller looks like. The structure is a CMOS inverter. Typically, it's the last inverter in a series of inverters, each one larger in area than the last. This is done in order to be able to drive capacitive loads while keeping speed of the device high. The largest inverter is the one we're looking at right at the output pin. So let's take a look at a really common MOSFET part for this kind of function, the BSS 123. This is the diodes Inc. version of the part, but lots of other manufacturers offer it as well. The upper left shows the FET in the off state, where the gate to source voltage is close to 0 volts. The first key datasheet characteristic for the state is the drain source breakdown voltage, which is 100 volts for this part. From our requirements, we're only going to have 5 volts from drain to source, so we're definitely good there. The other key characteristic for the off state is the 0 gate voltage drain current. This is the leakage current. So 100 nanoamps at room temp and 30 microamps at 150 C is pretty good for a MOSFET. The trade-off for the low leakage is the high drain source on resistance, or RDS on. This is in the 10 ohms or so range, and this would be high for a FET that's carrying current, but it's more than sufficient for an enable switch where the current that we're talking about is likely going to be below a milliamp. Last, the gate threshold voltage is provided here too, and nominally for this part it ranges from zero point 0.8 to 2 volts, so this should be good for the 3.3 volt microcontroller rail. So let's start the design. So one thing that always needs to be considered is the state of the driver during turn on or after a reset. During this time, pins will often be in a high impedance or high Z state, and usually remain that way until program code executes and initializes the GPIO into its desired state. Generally, when the GPIO is in high Z, it's configured as an input. However, an output configured GPIO can also exhibit high Z if it's not driven high or low. So the GPIO configured as an output is shown on the left. So in high Z, neither the P or N channel FETs of the CMOS pair turn on. CMOS FETs also have drain to source leakage, similar to the BSS 123 MOSFET datasheet we just looked at. We can model leakage as resistors, where the P and N FETs will form a voltage divider when they're turned off. When the GPIO is configured as an input, the structure is still a CMOS inverter, but the exposed part at the pin is the input to the inverter. In this case, there are also leakage paths to the rail. One path that is easy to see is the gate to body leakage. The body is typically connected to the respective voltage rail. So again, a voltage divider is formed. So outside of the microcontroller is the gate of the MOSFET that we're trying to keep off our enable switch. Because of the leakage paths and voltage dividers, the gate of the FET can build up charge and potentially turn on. So the solution is to add a pull-down resistor. This resistor will ensure that the voltage at the gate will stay low and prevent the MOSFET from turning on during power-up, reset events, or any other time that the driver is in high Z. Typical values for a pull-down are 10K to 100K. You can go for a 10K resistor for a stronger pull-down, but the trade-off is there'll be a little bit more power drawn when the FET is actually turned on. Even with a 10K pull down, the current is below a milliamp, but that can still matter if you're trying to design something to operate from a coin battery, for example. The other resistor that's good to add is a source termination resistor. Typically, these will be in the 20 to 200 ohm range. Um, these are good for two reasons. One is that they slow down the edge of the turn-on signal, and that helps with signal integrity. And the other reason, and this is specific to PCB designs, is that it separates connections to and from any complex logic devices like microcontrollers and FPGAs. Having a resistor in the path helps with troubleshooting when something isn't working correctly, since it allows you to isolate the components, and it serves a protective function as well. It they're not really worth using if it's just a breadboard design, and there are plenty of other reasons not to include it, such as cost or high-speed designs. It's just whatever makes sense for your design. When you're doing layout, the source termination resistor is placed near the microcontroller output, and the pull-down resistor is typically placed near the enable MOSFET. You might go outside the 10K to 100K ohm range if it makes sense for your design, but let's say we want to lean on the power efficient side of the trade-off and choose a 100K resistor. If we use a resistive model for the leakage, we can turn the microcontroller GPIO stage and the MOSFET into a circuit that looks more like what you'd see in intro-level electronics classes. There's two methods for solving this that are shown here. One is setting up the KCL equations, and the other is to use Thevenin voltage and resistance. You simplify the circuit, and then you solve it with voltage divider equations. Either way works, just a preference. Um, if you solve this, it'll show that the enable voltage will be below 300 millivolts when the microcontroller is in high Z because of that pull-down resistor. From the datasheet we just looked at, it's well below the 0.8 volt threshold voltage for the MOSFET, so it will stay off. It's worth noting this is a simplified model or illustration, so it's not 100% accurate, but it's useful for understanding high impedance states and why pull-down resistances are added. The resistors chosen for the leakage represent a very leaky structure, maybe at a very high temperature. And leakage also doesn't really behave like a true resistor, but this is still a useful model when you're first learning about this. Another item that can impact design is the output resistance of the GPIO driver. You can find this from the digital output voltage values given in the datasheet for the microcontroller you're using. For this one in particular, it lists a few test conditions, and the highest resistance ends up being the 2.2 volt 1 milliamp test case, which is 250 ohms. So while the high Z state that we just discussed shows you why using a weak or high resistance pull down is a bad idea, this output resistance bounds the other side of the pull down. If for whatever reason you chose to use a 500 ohm resistor for a pull down, it should be clear that with a 250 ohm output resistance, the 3.3 volt at the rail will be reduced significantly by the time it gets to the gate of the FET due to the voltage divider that forms. So the 10K to 100K pull down range stays an order of magnitude or two from resistances that will cause problems with turn on and turn off, and it has some margin against part and environment variation. The estimated output resistance can also be used to see what the on and off states of the GPIO output look like. The redrawn textbook-like circuits are provided here in case you're pretty new to circuit analysis or design. But because we have strong pull-up or pull-down paths through the 250 ohm resistors, the actual voltage at the gate of the FET should be very close to 3.3 and 0 volts respectively. For parts other than the BSS 123, there's some common parts listed here, both the MOSFET version that we just looked at and for BJTs as well. You've probably seen at least one of the BJT part numbers before. These are SOT23 package parts meant for layout on the PCB, but you can find similar through-hole parts for breadboards. One thing to note is you can have the same part number made by different manufacturers, and sometimes characteristics will be slightly different. For example, most 2N702 parts will have a max threshold voltage of 2.5 or 3 volts, but some manufacturers do list 2.0 as the max. Typically, MOSFETs designs can be made to be more power efficient, but BJT designs can be more robust in terms of ESD susceptibility, noise immunity, and worst case performance. So let's take a look at a BJT datasheet for a really common part you may have seen before, the 2N3904. This is the diodes Inc. version of the part, and again, other manufacturers offer it as well. The upper left shows the BJT in the off state where base current is negligible and base to emitter voltage is close to 0 volts. The first key datasheet characteristic for the state is the collector emitter breakdown voltage, which is 40 volts for this part. Again, significantly higher than the 5 volts we expect to see. The other key characteristic for the off state is the collector cutoff current, which is the leakage current. 15 nanoamps is a little better than room temp performance of the BSS 123, but that may not stay true at high temp since leakage typically doubles for every 10 degrees C rise in temperature. For BJTs, there's no on-state resistance, that's provided. Instead, data sheets give collector emitter saturation voltage. And the base to emitter saturation voltage is also given. That's the 0.7 volts you're always told to assume in class, which in reality does vary quite a bit as the datasheet states. Even with high base and collector currents, there will be less than a volt from base to emitter when the BJT is on. So this should be good for our 3.3 volt microcontroller drive. The graph on the left, it's pulled from the datasheet to highlight two items. One is that the test condition for saturation voltage shows an IC over IB ratio of 10. This is typically the recommendation for using BJT as a switch. The other item worth highlighting from this graph is that it's using 0.1 milliamps as the minimum current. When you're working, using parts within datasheet limits does make your life easier, so we'll use this as the limit. And in fact, we'll go slightly beyond the minimum and size R2 to give us zero point 0.2 milliamps at a 5 volt input. So R2 will be 25 kilo ohms. So that means our collector current is 0.2 milliamps. Then at the absolute lowest, the base current should be 20 microamps. You can make it higher. In this case, we'll make it 100 microamps. The design equation setup is shown here using the fact that microcontroller drive is at 3.3 volts and the enable voltage is 0.7. One caveat is that not all current coming out of the microcontroller pin will go to the base of the BJT. Some of it will flow through R4, so we have to subtract this from the base current. To simplify the algebra, we can remove the output resistance of the microcontroller from the equation since it's fairly small, and assume that R3 and R4 will be the same resistance. So solving for R3 in this case, you get about 19 kilo ohms. And you can go ahead and set R3 and R4 to 20K, but since R2 is a close value, you can just use 24.9K for all three parts in order to keep the number of different parts in your design down. So here are both BJT and FET enable switch designs. For the BJT, we end up with 80 microamp base current and 200 microamp collector current, ensuring strong saturation of the BJT. For the FET design, only 33 microamps is coming from the microcontroller pin, and the drain current is 50 microamps. So this design is a bit more efficient. Both of these designs should work, and there should be enough context now for making your own decisions